Hi, I'm Guille. Probably you know me. And I'm here to talk to you about improving snapshots in Pharo. Of course, I am again just a proxy. Most of the work that I'm going to show you is being done by Pablo and Nahuel. So I'm just in the same room and asking stupid questions all the time. But they are the main doers. So there is the smart thing. So we know and we love to say that, yeah, everything is an object, so numbers, characters, strings, arrays. Yeah, so everything is an object. Then we have closures. They are objects, and that's actually very good because we can manipulate them. We have classes. Also, methods are objects, so there are a lot of methods there, and each of them is an object. We can talk to them. We can do stuff. We have the ASTs. So we have all the literals in the methods that are objects. So everything is an object, and we have a lot of them. Yeah? So it's lots of objects. So that's not a bad thing per se. The thing is that having lots of objects also means a lot of stress. So we have stress for the garbage collector, stress for the auto-completion, for searching stuff like in Spotter. We have the startup is also stressed by this because there are things that need to sometimes traverse graphs of objects. So having a lot of objects sometimes can be a challenge. Yeah? So 2 years ago, I don't know, so somebody will tell me something more precise, we started to work with Liveware, so the consortium started to work with Liveware on large image support to be able to work with images that have several gigabytes of code. Yeah, so lots of code, lots of methods, lots of classes. So there is the package. If somebody wants to get it, it's MIT. I will highlight some of the stuff that was being done during last year or 2 years ago. I don't remember now. I'm old, sorry. So the main highlights is that we have generator-based searches that give a kind of a stream API to look for stuff. So this is the main thing in there. So for every kind of search, we are going to build a generator that is going to just iterate over entries and yield elements one by one. So like that, you can express searches in a sequential way while it actually works like a stream. Yeah? And there is another of the highlights is a GC fine-tuning API that helps to configure stuff like the size of the Eden or the GC ratio. So how often is the full GC going to run? How do you want the old space to grow or to shrink and stuff like that? Yeah. So this is all MIT and open source, so you can get it and try it, read the documentation, give us some feedback. But still, we have a lot of objects. Yeah. So and the situation got improved, but still we need some stuff to do there. So we all know that one of the things that people will say is that we are working with images. So what is an image? So we take all these objects, we put them together, we shake it a bit, and then we put them in a file. Yeah. So that is the image. So I'm going to call it snapshot. Yeah, we take a picture of the objects of the heap, and then we store it. And then all those objects are here, and this can be, so the default image that we are distributing in Pharo is around 50 megabytes or 40. Marcus knows the exact number. It can be gigabytes, I don't know. And this is designed right now based on a couple of points. So these images are created once, they are bootstrapped once, and then we mutate them. Yeah, so once the first image is created, we generate one of them in each continuous integration run. And then you take it, you load it with the virtual machine, and then you work on that, and then you save it. Yeah, so that's how it works, and then you save it, you reload it, and you work and stuff like that. And this work can be loading code, creating objects, running your application, maybe running the GC, and then repeat this process. Yeah, so this is what we do all the time. Now, what's the thing with this is that there are some bottlenecks in performance here. So these loading images, saving images, and sometimes running even the GC can be slow, even more for large heaps that can take a couple of gigabytes. Yeah, because of course, If this is a couple of gigabytes and the model is not good, then that means that starting an application will be bound to the speed of your disk. So it can also take a couple of seconds to GC because you have to traverse the memory and so on. So why is that this saving and GC and storing or snapshotting is slow? So let's first understand how the model is it behind. Yeah. So inside the image file, we are going to store all of your objects, so your application and system objects, and the threads, so the processes and the context, so you can then, once you load, continue executing stuff. Now, when the virtual machine is running, you have several pieces of memory, segments of memory. You have one piece of memory that has the JIT compiled code. You have a piece of memory where you have the stack, so this is the stack memory. Then you have the heap, where you have new objects and the old objects and several generations there. So this is OK. And now, when we are loading an image in the virtual machine, what happens is that we take this and we just put it in there. We drop it in the old space. Yeah, so this is actually directly mapped to the old space. So that means that when the virtual machine starts, the JIT machine code is empty, the thread stacks they need to be rebuilt from the objects that you stored before, so from these guys. And the new objects, they start empty, so there are no young objects. So that means that actually we start with a cold VM. The startup is slow. Maybe when you saved your image, you had a lot of methods that were JIT compiled, and they are not there anymore. There are also some other things that can impact performance, like what happens if the operating system doesn't give you the exact same address where you're going to put these segments. So if when you were running the first time, you were allocated here, and suddenly in the next time the operating system gives you some other address, then this delta will actually impact all the objects that are here, because here we store pointers. So you need to remap all the pointers. So this is called reference Swizzling. So we need to traverse all the heap and map every pointer by a delta. Yeah, this is because we are storing here pointers, and we don't have a kind of an object table or stuff like that. And this can be very slow for 2-4 gigabytes images or snapshots. So what happens when we do the other way around? So when we want to save something. So the first thing that happens is that we discard the JIT machine code. Why? We don't save it because it's not portable. And images were thought to be portable. Like, I can create a snapshot, send it to somebody else that is maybe running on a different architecture, and then, yeah, OK, my machine code is not quite the same. Also, the JIT machine code can have absolute addresses, and maybe you don't want absolute addresses there. So, or maybe the machine code has pointers to the objects in here, so you have to be really careful. So to avoid all that mess, right now we are discarding it. And then we have all these stacks that are here that are optimized, but we don't save the stack as it is. We just create objects from them. So we have to reify the objects, the contexts, and we have to save them in the here in the new space. And then we run the garbage collector. We promote everything that was here as old objects. So that means that here, the generational stuff, we lost it. And then we save the old objects to the disk. Yeah? So that means actually that we are losing all the optimizations that we were doing. We lost the machine code that we were building. We lost the native stacks. We also lost this information that there were some objects that were about probably to die. Now they are old, and they are not going to die soon. Yeah? So this is, OK, this worked for a long time. But I think that we can do better. So we started a couple of months ago, maybe 6, 8 months, to work with Pablo and Noel, with a couple of other goals. So we wanted to have faster loading, faster snapshots, and faster multi-gigabyte heaps in general. Yeah? So the idea is to improve in here, and potentially in here. But these two are really critical for us. So now we are working. So this is work in progress. And I'm going to talk a bit about things that are still a bit shaky, but we are getting good prototypes. The first thing that we're doing is going towards a different kind of image format. So you are not going to save your heap inside a single file. The idea is that they can be, you can have different segments in different files, and they can be each of them stored separately. So why cannot we reuse the native thread stacks and the native machine code that you compiled in the previous run? So the other thing is that having these guys completely separate can allow us to do much more easily mmap, so memory mapping using the system interface, to actually not guarantee, but have higher guarantees that they will be allocated in the same space. And if they are not, then we can actually fall back to a slower mechanism. But the idea is that we want to reduce the Swizzling, or minimize the possibility of the Swizzling, and to have lazy loading of memory segments. So if we start cutting in segments, we can load in different, so we can load lazily different segments. So this kind of architecture will allow us also to have different segments, or new segments. So for example, to split the old space into separate segments that can be stored and loaded separately and independently. And one of the other things is that we can have, for example, one of the projects that we're working on is to have a separate space of permanent objects or semi-permanent objects. Yeah? The idea is that we have a lot of objects that they don't move a lot. Yeah? So I will go in details now in 1 minute. But with that knowledge, one of the things that we can do is to reduce pressure on the garbage collector. Because we know that there are objects that don't move, they don't change. So why we need to work on them, why the garbage collector has to go over them. Yeah? So, and that is the main idea of this semi-permanent heap segment. So we have a lot of objects, and some of them are red, so they are not moving, will stay there, like methods, classes, and stuff like that. So when we run the full GC, we still have to actually traverse this entire thing. So these things we are traversing them a lot for nothing. So how can we reuse that knowledge? So the first idea here is to separate these permanent objects from the old objects, the normal old objects. So the first thing for example, if we draw a line here and we split objects in between permanent and old, one of the things that we see is that the permanent objects, they need to be roots also of the old space. Why? Because if we don't iterate or we don't know anything about these guys, actually this guy is going to be collected, the guy here. But we don't want that guy to be collected. So that means that we need to somehow know that this guy that is permanent knows this guy that is old. And the same thing with this and all this graph. So no, the thing is that not all of them are roots. So actually, I don't want to store all of these guys. I just want to store these guys. Yeah? Because if I have to iterate all of these guys to know which old objects I need to collect, then actually I didn't win anything. Yeah? So that is the worst case scenario. If all of the permanent objects are roots actually of the old space, then we didn't win anything. So what we need to do is somehow maintain a remember set. What is a remember set? It's a set of objects that remember objects in the old space. So these are the green objects. And these green objects, they need to, so if we track only the green objects, then every time that we are going to collect the old space, we just need to iterate all the green objects. And then it should be much cheaper than traversing all the red objects. Yeah. So this is a kind of standard technique for garbage collector building, but now we are maintaining a remember set between the permanent space and the old space, and we are maintaining it with the write barrier, and then so we are updating it in the write barrier and cleaning it during GC. Yeah, so this is kind of standard thing. But okay, so we have this. That's okay. Another thing is, okay, we want to select what are the objects that are going to be here. Because we start with all objects as blue, and then you need to somehow decide which are the ones that you're going to move to the red space. Yeah? Which are the ones that are red? And in the worst case, of course, as I told before, if they are all permanent, if we do a bad selection, so here are the arrows, it is not necessarily representative. But the point is that if we do a bad selection of objects, we can have a worst case where all the objects that we selected will be remembered, and then we didn't win anything. So we need to have a good selection of objects where we minimize the remembered objects. So the question is really, how do we cut this space? How do we discern, OK, you are going to be there, and you're going to be here? And this boils down to how do I minimize the remembered objects. I want to minimize the objects that I remember while I maximize the number of objects that are here as permanent. Yep. So this is not so easy because, first, for example, right now, without changing too much in the virtual machine, nil, true, and false, they live in the old space. Yeah? So if we want to move them around, we need to change a lot of code. But that means that if we don't move them and we let them in the old space, then every object that knows nil, true, or false will be in the remember set. So maybe it's not worth to move objects that know nil, true, or false. So also some things like, if you make a class permanent, well, maybe you want also to make the method dictionary permanent. And maybe you want to make also the methods and the literals. Otherwise, at the end, you will just have a really big remember set. So we need some kind of heuristic to decide. So we started working with some manual selection with Nahuel a lot. The idea at first will be to have, for production applications, a kind of an heuristic selection of objects. So for example, some of the heuristics that we are using right now is, OK, we are going to move code-related stuff. We are going to move objects, classes, methods, method dictionaries, meta classes, and stuff like that. Some other heuristics that are actually needed to have a good selection that we saw so far is that collections need to go with the inner array. Otherwise, if you have an ordered collection that has an array, then if you move just the ordered collection, then the ordered collection will be always in the remembered set. So you have interest in moving also the inner array. Something that also worked for us is that association, when we move an association to the old space, to the permanent space, sorry, the values of the associations, we don't move them by default. So if you need to move them, so that needs to be done case per case. So based on some of these heuristics, so we built some kind of automatic packaging or automatic moving of packages of code to the permanent space. And we did some experiments. So the first thing that we measure is, OK, what happens if nothing is in the permanent space? So here, so this is our baseline. It's 100% of objects are in the permanent space. So the garbage collector takes 1, so it's relative. And what happens if we move the kernel package only? So you move object, you move numbers, so a small integer, and all the related methods and so on. So actually, only around, I don't know, how much is it? 3%, 4%? Yes. So 4% of objects, or 4% of the memory is occupied by permanent objects. And then the rest is still old space. And we see a little degradation of memory. There are probably locality issues there, because now you have to, before you iterated all the memory from beginning to end, and now you have to jump around reading remembered sets. But as soon as we add all packages, or almost all packages, yeah, so we see that actually the memory occupation now gets, so the permanent objects are, the percentage is much higher. It's still not 100%. But we can get GC speed ups of 2 times, which just, so it was probably 2 afternoons of work of selecting what is there. Yeah. So this is a potential. The idea is that, OK, maybe you want to use these kind of things in your production applications. When you have your application that is deployed in a web server, well, your classes are not going to change. So yeah, you can move everything to permanent space, and then you run your application and have a very good GC, or lower a lot the poses. So the next thing that we are going to do, or we are working already, using this infrastructure to select objects and using heuristics is to do automatic object selections. Yeah. So the idea is that now what we are doing is we are running simulations. So we take one object, and the idea is, OK, what is the next object that I have to add to the permanent space from this initial object? So like that, with the permanent space grows, and the remember set still keeps low. Yeah. So that is the kind of idea. So we want to estimate automatically the permanent segment size and the remember set size to try to maximize one and minimize the other. Yeah. We also, in our simulations, we have some debugging tools to understand when something doesn't work well, what is leaking? What is the object that is in the permanent space that is not being, that is being referencing wrongly, or a lot of objects in the old space? So why is this object in my remembered set when it shouldn't be? Yeah. So the idea is that with this, we want to make automatic heuristics to be able to have even better selection for production code. Now, one of the other things that we are working on, so Pablo is the guy behind this, is that once we have this idea of, OK, we can have really separate segments of memory, why not sharing them? Yeah. So actually, this is the main idea is to share, for example, the permanent objects between several processes. Like, why don't you share the object, all the kernel classes of Pharo between many images? They will take less space in memory. They will take also less space in disk. And they will also make the loading of the images faster. So because they will be loaded only once. So the idea is to be able to share all these kind of immutable objects. And then if you need to change them, we do a copy of the heap or this segment on write. Well, the idea is to be able to scale multiprocess applications and to do even application-specific permanent object selection for you in general. So some final words. We are hiring. I already said it. We are looking for people. If you know somebody that would be interested in doing this kind of stuff, come to talk to us. Again, the keywords are compilers, interpreters, memory management, security, stuff like that. And thank you very much. One slide back. Ah, you want to? Yes. Good. Thank you. What? One more? This? OK. Questions? Yes, Casper.
You started the talk by saying that it was unsafe to save the Git compiler methods. And then the next slide, you saved the Git compiler method. And there was sort of a discord there.
Yeah, so yes, I don't, let me rephrase. So it's unsafe. Well, you need to take care about it first. So it can be made safe, yes, I think. So as soon as you can remap references to the heap, if there is a need, it's not a problem. The other thing is that right now it's not done mainly because nobody took the work for doing it. So so one of the issues why it's not done right now, it's because probably safety issues. But the other one is that because nobody did it, so nobody just made effort. So the idea is that we would like to move forward in that direction. But I don't think that there are any really safety issues. So yeah, we can talk about later about security issues. But we store machine code all the time in all our machines. So
that means if you save it on a M1 machine and I load it on an Intel machine, that part is just discarded?
Yes. Of course, I will not run my M1 and my ARM64 code in your Intel machine. No. Yes, that doesn't make sense.
It's just thrown out at a later point in time.
Yes.
Okay.
Nobody else? Steph. Yes.
Do you think that we can get better there?
Maybe, probably. Then the question is, actually, I would like to experiment with larger images. So this was done in the standard image that we are distributing. So probably I would like to see what is the impact in 2 GB images that have a lot of code. The other thing is that here we only were selecting code-related objects. And what if we also, because the GC does 2 things. So it's a mark and compact. So it does first an iteration to mark objects that are used, and then it compacts the memory. So one of the problems with the compaction is that here in the heap, we are here in the old objects, we are mixing normal small objects and large objects, and large opaque objects like big bitmaps and stuff like that. So it would be actually make sense to have a separate space also for opaque objects, large opaque objects, mainly to reduce also pressure during compaction, because otherwise you are just moving a lot of data, and even if it is easy to do, it's slow. Yes?
But each time you add a space, normally we
Space, a hole.
like
A new of this, okay. Yeah, a new segment.
you have to do more checks.
No. The point would be that, for example, a large object segment can work like an old object segment. So a large object segment is an old object segment. So regarding remember sets and stuff like that, it works the same. The first thing that happens is that maybe you just need to not compact the other one, the large objects, but you need to iterate and mark them. The second thing is that since the opaque objects, they don't have references to other objects, then actually it simplifies a lot of other things. So you can make assumptions in that space that you cannot make in this guy. So. Thank you.